We need to talk about more chromatography. And I know that you love listening to all of these lectures and to me, and that's why you're coming back for more punishment. So the next one is going to be called molecular exclusion. And if you exclude something, that means you leave it out. Boo hoo hoo. My feelings are hurt. I've left out something. Well, what do I leave out? It's based on size. So size does matter, people. And that means that in the chromatography world, size is going to play a very important role on how quick things can move. All right. So with molecular exclusion, what happens is that you've got a column that's going to be here. And let's say that this column has different size particles in it. Let's say that we've got some really big old fat ones all the way up and down. And then let's say that we've got some tinier ones that kind of fill in the crevices a little bit and maybe even tinier. But the concept here is that this is a piece of Swiss cheese. All right? And this piece of Swiss cheese will allow these components to separate and to go through from each other. So let's say that I've got a sample up here at the top. And let's say that part of my sample has a big O particle and the other part of the sample has a little bitty particle. Okay? So what happens here is that if this little bitty particle kind of enters into the column, what you'll see is that that little bitty one can get in all the nooks and crannies. All right. So this little bitty particle will take its time and it will go through here and it will kind of bounce around back and forth. And it will say, oh, look at all of these little nooks and crannies that I can find and do stuff in. Oh, I love playing in the playground of the stationary phase. And then eventually, sooner or later, it will come out of the column and out the other end to get detected. All right, well, if a big particle comes through, that big particle is going to take a look at this column and it's going to be entered in and it's going to say, I can't fit in the nook and crannies. Therefore, I can't go through the column as fast. Or can I? That's always confusing to people, right? So if you think about it, the small particles go into the nooks and crannies much, much easier. And because they can go into the nooks and crannies, they spend a very long amount of time in the column before they go out the other end. Well, if these big particles cannot spend time in all the little bitty nooks and crannies, it just basically blares its way through and says, I don't have time for that mess, and it's going to go straight through the column. Then molecular exclusion typically allows the larger particle to go through first. And that's because it can't play around, right? The smaller particle can play in all the nooks and crannies, and it will come out last. That's traditionally kind of the run-of-the-mill electron exclusion that you will see set up in a laboratory if they're deciding to use molecular exclusion. All right? So it's a piece of Swiss cheese, or if you really want to think of it maybe in a little more detail, think of a sponge. A sponge at home, a natural sponge maybe. You've got some big holes, you've got some little bitty holes, and it's all this network of openings that's inside of that sponge. And there's just too many things and too many small areas for these larger molecules to be. And that's why we can separate things based on molecular size when it concerns molecular exclusion. Okay. Two other words that this chromatography technique can be called. Instead of molecular exclusion, we can call it size exclusion. That's also acceptable. And if I don't want to use molecular exclusion and I don't want to use size exclusion and I really want to be particular and grumpy about it, then gel filtration can also be a possibility. So gel filtration is the same thing as size and molecular exclusion. They're all three basically talking about the same thing. Okay. Finally, we're going to talk about affinity chromatography. And in affinity chromatography, we're going to see a little bit of change here. This is completely different than some of the other chromatography techniques that are out there, and we're getting ready to tell you why. Aren't you suspense? Yeah. Okay, so with affinity chromatography, we have a column, and this column is filled with stationary phase. Okay, the difference here is that the stationary phase is basically a molecule that has some type of functional group on the outside. And that functional group is basically targeting one specific component. This is kind of tailor-made in a way, right? We get this column, we put a stationary phase in it. This stationary phase is only going to reach out and grab one component, and that is it. So you really need to figure out what you want to do with the affinity chromatography system. What do you want to capture? Because typically it's only one thing that you will be able to reach out and grab, and the rest of it will go straight through. All right? So you'll have a component up here at the top, a mixture with different components in it. And that will go into the column and it will go out the other end. That's normal. That's what chromatography is. The problem is that we're not relying specifically on polarity to do the separation. Everything will go out. Everything will basically breeze through this column except for one thing. And that one specific thing is what I'm searching for and what I want to analyze. Okay? Once I send my sample through and everything comes out, what happens is that that one component is kind of stuck on the surface in here. And it can't leave. I can keep flushing this stuff with mobile phase over and over and over and over, and it's never really going to bulge or budge. Right? Okay, so that's how this chromatography system's a little bit different again. Because in all the other chromatography systems, I really didn't need to do anything. Once the sample went into the column and once it started to separate on me, then I just allowed the separation to take place. But in this case, what happens is that the sample comes in, everything leaves, and my component that I'm trying to measure really has been glued onto the surface of these particles, and it's going to be very difficult for me to get them off. So normally what happens here is that in affinity, I have a second round, and that second round is a different mobile phase number 2. And that second mobile phase will come in and it will take these components that's been really super glued to the surface now, and then it will remove them out, and then I can capture them here at the very bottom. Okay, so it normally is a 2 mobile phase system. The first mobile phase just pushes all the sample through, and that one component gets stayed behind. And then the second mobile phase, I put it in, and then bam, all at once, that component will come out for me to measure. All right, the Affinity Chromatography series and the Molecular Exclusion Chromatography series, you're going to find mainly in these biochemistry and biotechnology labs. That's where we see the majority of them. And the reason is because they work very well with proteins. They work very well with DNA. Any larger molecules that's traditionally outside of what you would call the chemist molecules tend to behave very well in affinity and very well in molecular exclusion. So we never really work with these. We don't do a lot with them. They are chromatography concepts that are out there that you might see in a laboratory at a certain point in time. So that's why we cover them. But as far as what you're going to be doing in our lab, you will not do anything with affinity or molecular size, at least not right now, right? So here's a diagram of the affinity, and you're going to see a mixture of proteins in this beaker, and they've turned them different shapes and colors, right? So we've got these blue squares and these yellow triangles and these red half moons. And that whole soup basically gets put onto the top of the column, and it begins to float through the column and out the other end. So we put the mobile phase on top, and that mobile phase is basically going to push everything through, and that's what you're seeing down here at the bottom. It's going to be everything that you do not want. We're not going to be focused on finding the concentrations of these or anything, right? We're just going to flush it out. And this filtering process basically will capture all of these little red half moons. Because if you look on the surface of the stationary phase, you see these little black orbs. And those little orbs perfectly fit on the half moon. They do not fit the triangles. They do not fit the squares. It's only the half moon shapes. So we've picked one specific stationary phase to do a job. That job is to capture, in this case, the half moon molecules. And all of that other crap gets out of the column into the waste containers down below. And then what I have to do is I have to go through with a second mobile phase. And I have to flush it out. So once I get rid of all the unwanted stuff, I then take a second mobile phase and I put it onto the column, and then it begins to dislodge all of those little red half moons for me. And I can collect all of those parts of the sample down here below in my collection tubes, or to analyze them just like I did before in all of the other chromatography systems. All right, so that's the story with affinity and molecular exclusion. Again, you're probably not going to work with these in our laboratory at all, but that doesn't mean that they're not very common in an actual working laboratory, because they kind of are. All right, so affinity and molecular exclusion. So that's where this video is going to stop. In the next one, we'll talk more about the pieces and parts of the column and the instrument, and a little bit more theory about what happens here as far as the separation technique goes.